Okay.
Vishwesh sir, please continue.
Okay. Welcome. Good afternoon, everybody. This is my great pleasure to welcome today's VSM speaker of this special series, Professor Gulab Dewangan, who will be talking about interplay between the disk and corona in active galactic nuclei. So, a brief introduction about Gulab. He joined TIFR 1995, and after doing PhD, went for a postdoc at Carnegie Mellon University, where he continued as a research physicist, and then returned to IUCAA in 2008. And since then, he has been bearing various responsibilities at IUCAA. So Gulab's interest in AGNs is manifold, particularly in narrow-range Cepheid galaxies. He investigates multi-wavelength AGN variability using data from multiple wavelength bands. He studies warm absorbers in X-rays. He has deep interest in disjet connections in AGNs. He studies the relativistic iron lines and so on. And other than AGNs, he is also interested in some X-ray binaries and ULXs and so on. So today's talk is going to be about interplay between disk and corona, which is the X-ray and UV emitting regions and line emitting regions in AGNs. So we look forward to Gulab, please.
Thank you, Vishwajit. I'm really happy to give this talk. Of course, I would have preferred to visit RRI. I really like the RRI campus and staying there for some time. But anyway, I'm happy to give this talk. So as Vishwajit mentions, I'm going to talk on the interplay between the accretion disk and hot corona in active galactic nuclei. So let me briefly introduce active galactic nuclei. Of course, the AGNs are the nuclei of galaxies which are active in some sense, and they produce large luminosity of the order of 10 to the power 42 to 10 to the power 48 ergs per second. They are compact, they are unresolved at all wavelengths. The size is much smaller than a parsec. These nuclei emit broadband continuum from radio to X-rays and gamma rays. Many of these AGNs show strong emission lines as well as broad emission lines in the optical and ultraviolet bands. AGNs, when we think of AGNs, the X-ray emissions appears to be generic characteristic of AGNs. Some of the AGNs also emit high energy gamma rays as well. Most AGNs are variable at almost all wavelengths, and they are strongly vary at shorter wavelengths or high energy radiation in X-rays and gamma rays. A small fraction of AGNs are radio loud. They show jets and lobes, and the sizes of the jets and lobes can be from parsec scale to kiloparsec and megaparsec scale for giant radio galaxies. Here I show some pictures from AstroSat. So this ultraviolet picture of NGC 4593 taken with the AstroSat's UVIT in the far ultraviolet band. And here you see the bright nucleus and the host galaxy, spiral galaxy as well. And this bright nucleus is of course the AGN. Sometimes this bright nucleus is not very obvious because there may be dustland or some kind of obscuration. So you don't see in the strong, bright nucleus in the ultraviolet or optical bands, but in X-rays, particularly slightly harder X-rays, because harder X-rays penetrate any kind of obscuration. So you see this bright nucleus in X-rays. This is what I call observer's view of radio quiet AGNs. Physically, we understand AGNs to some extent. Basically, the high luminosities of AGNs translate to large black hole masses, if you apply the Eddington limit, because any object cannot emit arbitrarily large luminosity. The radiation pressure force generated must be balanced by the gravitational force, and that gives the Eddington limit, and that gives us a limit on the mass, and that turns out to be huge mass, million to billion solar masses. And now, of course, we have a pretty accurate measurement of black hole masses using the reverberation mapping technique in the optical band, and that also, of course, tells us that the masses are large, 10 to the power 6 to 10 to the power 9 solar masses. These objects are, of course, very compact, unresolved, and one can put a limit on the size of this object by using variability time scale. Some of the agents vary on a few hundred seconds time scale, and that tells us that the sizes of this object must be very, very small, very compact. So essentially what we are saying that there's a huge mass which is confined into a very small region. And in physics, we know nothing any other than the black holes. So what we say, this is the black holes, and the accretion onto supermassive black holes powers this active galactic nuclei. So just to remember a few of the numbers, so AGNs have these masses of order of 10 to the power 5 to 10 to the power 10 solar masses. They are powered by accretion with a luminosity, which you can write as eta times m dot c square. M dot is the accretion rate, and eta is the efficiency. And this efficiency is of the order of 10%. It can be higher also, of course. The size scale, which one can think of Schwarzschild's radius, which is 2 gm by c square. And the luminosity is typically of the order of Eddington luminosity, or somewhat lower than that. When we think of the AGN central engine, so AGNs have several different emission components, and these large number of emission components actually gives rise to a variety of different types of AGNs. I will not go into the details on this, but to briefly tell you that we have, of course, a supermassive black hole which may be spinning, and that accretes material from the host galaxy and forms an accretion disk. Above and below this accretion disk, there are this line emission clouds, which are called the broad line region clouds. And of course, in the innermost region, there is a X-ray emitting region as well, which I will discuss. And there may be the jets emanating from from the very close to the black hole as well. The region, this accretion disk and the broadline region clouds, etc., are surrounded by a torus-like optically thick torus, which is also cold. So this gives rise to different kinds of components. For example, if your line of sight is passing through this torus, then the entire accretion disk, the hot corona and the broadline region are obscured from our view. So they look very different. On the other hand, if your view is direct to the this accretion disk, X-ray emitting region, and this broadline region clouds, so we see all this emission from all these components, and in that case, we call these AGNs as type 1 AGNs. And then, of course, there are Seifert type AGNs and quasars, etc., and all of them are classified in type 1, type 2, etc. Okay, and if you go further away, then of course there are other kinds of line emitting clouds, which are called narrow line region, which you observe in the optical ultraviolet band. So in this talk, I will be confined to the innermost region where the accretion disk and the hot corona are there. We do not understand the exact geometry of this accretion disk and the hot corona, but what we think that, of course, there is this accretion disk surrounding this supermassive black hole, and in the vertical direction and the symmetry axis, there is likely this corona, which probably can be the base of a jet, or it may also be confined in the innermost regions where the disk may be truncating at somewhere, and the inner region may be filled with this hot corona. We do not know exactly, and different types of objects may have these different types of accretion disk corona geometry as well. So let's see how does this accretion disk emits, and even the hot corona, what kind of spectrum we observed from accretion disk and hot corona. This accretion disk essentially is formed due to the conservation of angular momentum, and the temperature of the accretion disk is not uniform along the disk, but the temperature is highest in the innermost regions, and it decreases in the outer regions as a function of the radius, and the temperature varies as r, the radius to the power minus 3/4. Okay, and at any given radius, the accretion disk, of course, is optically thick, and therefore it emits like a black body with a temperature given by this radius dependence. So accretion disk may be thought of as a series of annuli, and each annuli emitting like a black body and with a different temperature given by this relation. And therefore, one can calculate the accretion disk spectrum as the sum of the spectrum spectrum of black body-like spectrum from individual annually, and the sum looks like this. In the intermediate frequencies, we have nu to the power 1/3 dependence. The spectral safe is 1 nu to the power 1/3. At high frequencies, due to the wind tail, the spectrum, of course, declines, and at low frequencies, due to the Rayleigh's limit is varies frequency to the power square. Okay, so we have this characteristic accretion disk spectrum, but this spectrum cannot explain the entire broadband. This accretion disk alone cannot explain the entire broadband spectrum. In particular, there's a strong X-ray emission, which cannot be explained just by the accretion disk. And that to explain the broadband X-ray emission, we need what is called this two-phase model. So we have this two-phase. One is, of course, the accretion disk, which is the cold phase with a temperature of 10 to 20 electron volt in the innermost regions. And there is a hot phase, which we call hot corona, and it is optically thin. And the temperature of this hot corona is about a few hundred kilo electron volt. So what happens then that the disk is emitting this optical ultraviolet photons, and these photons interact with this hot electrons or energetic electrons in the hot corona, and they get inversely Compton scattered. So they go through repeated inverse Compton scattering, and in that process, that one generates this X-ray power law kind of emission. So in simple terms, so one can understand as follows. So if you consider this accretion disk spectrum more like a black body kind of component, then you take a fraction tau. The tau is the optical depth of this hot corona, and then that is upscattered to energies given by this factor 1 + 4 kTe by MEC square in one Compton scattering step. Okay. In the next step, again, you take the same fraction tau of this black body-like emission, which has been scattered, and then again upscattered by the same factor 1 + 4 kT by MEC square. And you repeat this process until the energies of the photons become comparable to the energy of electrons in the hot corona. And once you sum all these components, then you have a power law-like spectrum, power law-like broadband spectrum, which cuts off at high energies, which is characteristic of the temperature of the hot corona. In fact, one can use this cutoff at high energy to measure the temperature of the corona, and people have done that using broadband X-ray spectrum. So you may think that this the accretion disk and the hot corona essentially of course makes the central engine of AGN, but these are too simplistic. There are lots of complications, particularly due to the interaction between this interaction or interplay between the accretion disk and the hot corona. I already mentioned that the optical UV photons from the accretion disk get Compton scattered. And therefore, there is a Comptonization delay which will essentially be the light travel time and actual delay due to multiple scattering here. So that is one kind of interplay. And once this broadband X-ray power law is formed by this Comptonization process, then of course we observe that as a broadband X-ray power law. But a part of that, it also illuminates this accretion disk. Then there are two important things. First of all, the inner regions of the accretion disk reflect some fraction of this illuminated X-rays, and that we observed as a reflection spectrum. And in the reflection spectrum, there is an imprint of this accretion disk in the form of some of the line emission, particularly the iron line, and that iron line is modified due to the spatial and general relativistic effects near the black hole, and that's how we probe the inner regions of this inner regions very close to this supermassive black hole using this reflection spectrum, which I will discuss a little more detail. Okay, apart from the reflection of some fraction is also absorbed by the accretion disk, and that's absorbed X-ray emission is thermalized. Therefore, the disk temperature may get enhanced a little bit and then re-radiated in the optical ultraviolet radiation, which we call as the reprocessed thermal emission. And of course, the disk will emit the intrinsic emission. So whatever we observe, that's the result of intrinsic emission from the disk and the reprocessed X-ray emission in the optical ultraviolet region. And this is something, yes?
May I ask a question?
Yeah, please.
So, what is the source of this corona? I mean, do people know?
This is something we do not clearly understand. I mean, one possibility, as I mentioned, is could be the base of the jet, and then the question will be how the jet is launched. Of course, there's some of the magnetic processes, blend force, Nazik mechanism, etc. People talk about, but exactly we do not understand this thing. Then even magnetic reconnection in the innermost regions in the disk that may also form a corona-like region. But to be frank, we do not clearly understand how does this corona actually forms.
And does people know like what is the extent of this corona for that matter?
What we know is that corona must be really compact, and there are strong observational constants. First of all, very simple constant is the variability time scale. The
Right.
broadband X-ray power law, which I mentioned, is varies on very short time scale. So the corona must be really compact. And then there are other observations which I'll discuss. The reflection spectrum, particularly, that also tells us that the corona is very compact. And there are very interesting observations, gravitational micro lensing observations as well. That also tell us the corona is really compact, of the order of about 10-20 gravitational radius. That's the limit. That's the kind of size of the hot corona we have.
Okay. Okay. Thanks.
Yeah. Okay, so if you look at the broadband spectral energy distribution of AGN, it looks like this. So in the optical ultraviolet region, there is a component which we call the big blue bump, and that is thought to be the direct emission from the accretion disk. And at X-ray band, in the X-ray band, there is this broadband X-ray power line emission, which I just discussed due to the comptonization process. In addition, there is a reflection spectrum which consists of this iron line at 6.4 kV. There may be features in the soft X-ray band as well. And there is a hump-like structure at 20 to 40 kV. So we see this reflection spectrum as well as this broadband continuum from AGNs. And in the soft X-ray band, if you consider from 0.1 to about 2 kV, there is another component which we call the soft X-ray excess component. And again, the origin of this component we do not clearly understand, but I will briefly mention the current status of understanding of this component. And in the near infrared, of course, that emission is a reprocess emission, which is by the torus. And I will not be discussing about the longer wavelength spectrum here. Okay, and to probe this, the accretion disk, the soft X-ray axis, as well as the broadband X-ray continuum, AstroSat is a useful mission, particularly for nearby AGNs, where AstroSat sensitivity is such that one can study only nearby AGNs. And the reason is that AstroSat is multi-wavelength mission, which has this ultraviolet imaging telescope, and it is sensitive in the far ultraviolet down to 1200 angstrom to about 2000 angstrom, then near ultraviolet 2000 to 3000 angstrom, and vis channel as well. And it has several broadband filters as well as low resolution gratings, which can be used to study this UV component, particularly the big blue bump component. And how does that connect to soft X-rays, which one can probe with the soft X-ray telescope, or which works in the 0.2 to 8 kV band. And of course, at high energy, at hard X-rays, we have the large area X-ray proportional counter sensitive in the 3 to 80 kV, and one can again use this instrument to study bright AGNs. Okay, and then CZTI is not really sensitive for AGN studies. So usually one uses the ultraviolet imaging telescope, soft X-ray telescope, and LEX-PC for the brightest AGNs. Okay, and I will show you some of this AstroSat observation. This is one observation of AstroSat, one observation with AstroSat of the Seyfert galaxy IC4329A. This is the second brightest Seyfert galaxy at hard X-rays, but of course it is much fainter in the ultraviolet and optical band due to lots of obscuration. So, of course, the AGNs are embedded in host galaxies. So they are complex objects sitting in messy environments. And one wants to probe the intrinsic emission from the AGNs, one needs to correct for this environmental effects in the messy environment. And that's not easy, because many things are actually uncertain. So particularly inferring the intrinsic ultraviolet emission is very difficult, and that intrinsic UV emission is what one uses to study the accretion disk. So here you see this this is the composite color image constructed from the UVIT data in the far ultraviolet, which is shown in green, the near ultraviolet, which is shown in red, and X-ray emission from observed with Chandra, because Chandra's resolution kind of is comparable to the spatial resolution of UVIT, and SXC resolution is much poorer, so it's not useful. So anytime you want to make this kind of the color composite image, so you taking Chandra image is very useful here. So you see this blue like dot-like thing here, nucleus. So that's the active nucleus, and you also see a dust lens passing through the central. So therefore, this is sitting in a complex environment, and one needs to correct for this dust lens as well as. And there is a lot of host galaxy emission in the ultraviolet, and that also needs to be corrected. So here we have tried to do all this analysis. First of all, we separate the host galaxy emission and the AGN emission by studying the radial profile and modeling the radial profile in terms of a point source due to the AGN, and the galaxy emission in terms of an exponential profile. And that's how we separate the AGN emission and the host galaxy emission. And when we do this, we find that we do not really detect have strong near ultraviolet emission. And the absence of this far ultraviolet emission is due to that obscuration, and this is also more like an intermediate Seyfert galaxy. So there is intrinsic obscuration here. So in order to correct for that, of course, one first corrects for the galactic extinction using this Cardilli et al. Law. Then one tries to correct for the internal extinction, which is much more difficult because this internal extinction law is much more uncertain. So therefore, in this particular case, we have used a number of different extinction laws by Sejourny et al. With different color axes that determines the amount of extinction from Balmer decrement, as well as by continuum modeling by other people. We have also used the Goskell and Wonker extinction law, as well as starburst extinction law, because there is a dust lens passing through, so there is lots of star formation as well, and that is why we use the starburst extinction law. And once you do all these corrections, then one also needs to correct for the contribution of the emission lines, because when you are looking at the ultraviolet band, there are lots of emission lines, particularly this carbon 4, magnesium 2, etc. And in between, there are also a number of emission lines, particularly the iron 2 complex, which cannot be decomposed in individual lines. So what we have done here, we have taken the quasar composite spectrum, and then we model the quasar composite spectrum in terms of a pure power law continuum and the emission lines, and therefore we can calculate the contribution of this emission lines into the UVIT bands, ultraviolet bands, which we have used for our observations. And that's how we infer the intrinsic continuum emission from this AGN. And when we try to describe this intrinsic continuum emission with the accretion disk models, this is what we get. So if we use the accretion disk around a curved black hole, which is and assume that accretion disk is extending to the last stable orbit, and also we consider the Schwarzschild black hole. Again, the accretion disk extending to the last stable orbit. Such accretion disk cannot explain the observed data here. But if we assume, if you make the disk to truncate at about 100 Rg, then the accretion disk, the intrinsic continuum emission is well described by a truncated disk. And these are the different curves and different data points are due to the different color axes, even for this Sejourny et al. Extinction law. And in the bottom panels, so there's different extinction law, Goskell and Wonker and starburst extinction law. So on each case, we need a truncated accretion disk to describe the observed far ultraviolet, near ultraviolet, and optical data from HST. So remember that here, because of the excellent resolution of ultraviolet as well as HST, we have separated the nuclear emission and have corrected for obscuration as well as contribution for the contribution of emission line, then we are getting this inferring that accretion disk is really truncated in this AGN at an inner radius of about 100 RG or so. So this is about this AGN, but there are other low luminosity AGNs which are probably also have truncated accretion disk, while the high luminosity ones, particularly the type 1 AGNs like narrow-line C-photons, etc., are most likely have an accretion disk extending to the last stable orbit. In particular, the broad relativistic iron lines do suggest, do imply that these some of other AGNs have accretion disk, full accretion disk extending to the last stable orbit.
Gulab?
Yes.
So I had a query.
Yeah.
This extinction correction, does this galaxy have a Spitzer observation, for example, 2.4 micron or at higher wavelength, 24 micron, 36 micron? Because then that can be used to correct the extinction from the galaxy itself.
Yeah, unfortunately, Spitzer observations are not available for this AGN IC4329A.
I see.
Yeah, yeah. Okay, so in addition to using the intrinsic optical ultraviolet continuum to infer the nature of accretion disk, one can actually use the reprocess emission in a model independent way to infer the nature of accretion disk in the following way. So let's say we have this accretion disk around the black hole, and we have this hot corona which is illuminating this accretion disk, and some fraction of this illuminated accretion disk is getting absorbed and re-radiated in the optical ultraviolet band. Because our accretion disk has a temperature profile, so the inner regions of accretion disk have higher temperature and the temperature decreases outside. So the reprocess emission in the ultraviolet band arises closer to the black hole, while the optical emission arises further away from this region. And if this is the case, then one can measure the delay between the X-ray emission and the reprocess of the ultraviolet and optical emission. And that delay will depend on the wavelength. For example, the delay will be short for the delay between X-ray and UV will be short, while the delay between X-ray and optical will be longer. And one can, using the standard accretion disk theory, one can actually find out what is the dependence of this lag on the wavelength of radiation we are measuring. So in a very simple way, one can consider the total luminosity emitted by let's say an annulus between R and R plus dr. So that will be 2 times this 2 pi r dr, sigma t to the power 4, where T is the temperature, because they're both sides of the disk are actually emitting. That's why you have to multiply by 2. And that, of course, will be balanced by the gravitational energy released between R plus dr and R. When the material moves from R plus dr to R, then this is the net amount of gravitational energy release. And then one can write this, derive this radius to the power 3 as a function of temperature here. And then one can simply, using basic relations like the Eddington luminosity, Eddington fraction, which is the fraction of volumetric luminosity and Eddington luminosity, and writing volumetric luminosity and an Eddington luminosity like this, and using Wien's law, one can convert the size scale here into the time lag, which will be the light crossing time, the speed of light into the radius, and derive this equation. And that tells us that the time delay is proportional to the wavelength power 4/3. And that is why if we measure the time delay, observationally we measure the time delay as a function of wavelength, and then look at the relationship, one can then establish that the accretion disks and AGNs are really standard disk. If there is some kind of discrepancy, then one can think other possibilities. So here is one example. This is a Fayral 9. This is a two-year swift monitoring observations in the UV, optical, and X-ray. These are the light curves. And you do need long light curves for some of these agents, because if the black hole mass is large, the time scales are long, and you need long observations. And these are the 2-year-long monitoring observations in different bands. The interesting thing is that you see a strong variability in X-rays, UV, as well as optical V band, etc. And when one cross correlates this and derives the lag and then plots as a function of wavelength, so this is the result. Of course, there are large errors because of the data quality, but then one can compare the theoretical expectations and the observations. So here the data points, so even with a linear model like the lag varying as a function of varying as wavelength linearly, then that can also explain the data, or it can also explain the wavelength varying as lambda to the power 4/3. But the important thing is that the lag, the magnitude of lag is longer compared to the expected from the accretion disk. Accretion disk model. So here in the accretion disk model also accounts for the illuminated flux, because when some fraction of the illuminated flux is getting absorbed, that will enhance the temperature, and that temperature will be given will be due to the intrinsic dissipation plus whatever is illuminated, and that fraction is absorbed here. And this is the temperature, and one can write down the time delay like this, and this is what is the relation shown here. This is for another object, NGC 5548 by McCarty et al. Here the error bars are much larger because the monitoring time scale was longer, better quality data, and clearly you see that the observed delays are longer compared to what is predicted from the accretion disk theory. And it turns out that the real accretion disk appeared to be roughly three times larger than the standard disk. And we do not know what exactly is the region, but this is what is telling these observations are telling us that the real accretion disk appeared to be larger. And this is not only from this kind of result. So there have been a few microlensing studies as well. So there also they found that the real accretion disk appeared to be roughly 3 times larger compared to what is predicted by Shakura-Sunyaev standard accretion disks. Okay, so what I want to say here from those observations, the temperature profile does seem to be like what is predicted from the standard disk, but the magnitude, but the sizes appear to be larger in these agents. So okay, so now again going to the talking about the interplay. So let's look at the X-ray reprocessing part and the X-ray reflection now. Now let's look at, we have already discussed about the X-ray reprocessing and how we can actually study the nature of accretion disks in AGNs. Now let's look at the reflection, because the illuminated X-rays, some fraction of illuminated X-rays are reflected by the accretion disk, and that one can use to study the innermost regions in this AGN. So the basic principle, the basic physics is like this. So we have this hot corona, that the emission from this hot corona is illuminating the accretion disk, and essentially the X-ray photons in the illuminating components are interacting with the disk material. And given the temperature of the inner accretion disk, the accretion disks are partially ionized. Hydrogen will be usually be ionized, but the heavier elements will not be fully ionized. So you have the K cell electrons attached, K cell, L cell, M cell, etc., attached with the atoms of the heavier of heavier atoms essentially. So in such a case, when an X-ray photon is interacting with, let's say, with an iron atom, then what will happen most of the time, this K cell electron will be removed due to the photoionization, and then there will be a vacancy here. Then the L cell electron will jump, and this will produce a characteristic line emission, which we call the K alpha line emission. In this case, iron K alpha line emission. Okay, and the iron is one of the most abundant element, and the fluorescence yield is also high. So we see that the iron K alpha line is the strongest line. There are also other emission lines like nickel, etc., but due to the lower abundance and for the lighter elements, the lower fluorescence yield, these lines are very weak, and most of the times they are not observed. At hard X-rays, first of all, this radiation above 7.1 keV is absorbed due to
This is Kinjal. Can I ask a question?
Sure.
Short. Yeah. So what is the instrument that is being used to make this observation? This Reynolds 1997.
This is actually not observation. This is a purely simulation. This is a theoretical work. But I'll show you the observations as well.
Okay. Thank you.
Okay. So just above 7.1 keV, due to the absorption due to iron, there is a huge deficit. While at hard X-rays also, due to Compton recoil, the hard X-ray photons lose their energy and move to lower energy. And the combination of these two, this photolytic absorption due to iron and due to Compton recoil at very high energy, gives rise to this hump-like feature, which we call reflection hump. So this is if you have an incident spectrum, which is like a power law. This is a log scale. So this linear line is essentially a power law. So if you have a power law incident continuum, then you see this characteristic reflection spectrum consisting of these features. And because this iron line is actually arising from very close to the black hole, that the shape of iron line is strongly modified, and we will see that how it looks like. So these are real observations. So this is an observation of one AGN called MCG 52316 by European mission XMM Newton. And here you see this line profile. This is again the observation of the same object, but at a different time and with much longer exposure time. So you see much better quality line here. What I want to say here that there are this narrow emission lines here, the K alpha line as well as the K beta line. These are the narrow core. But in addition, you see a strong, broad iron line. And if you calculate the width of these lines, so the full width at half maximum turns out to about 50,000 kilometers per second. Okay, that's a much larger compared to the velocity width, typical velocity of width of about 5,000 kilometers per second from the broad line region. And that is the much larger velocity component that definitely tells us that this must arise very close to the black hole from the accretion disk, in fact. Okay. How do you get this broad emission line? So let's see this. So if you consider an accretion disk and these two annuli here, and let's imagine these two annuli are emitting this line emission. And just due to the rotation, if you apply Newtonian physics, the line profile will be a double horn kind of profile. Okay. Now, if you apply special relativity, there will be two things. Due to the transverse Doppler shift or the time dilation effect, the entire line will move redward. Okay. And the line component, which is coming from the disk, which is moving towards us, and that component will be enhanced due to the relativistic beaming. Because in the rest frame of this disk, the radiation, of course, will be going in all 4-5 directions. But when it is moving with relativistic speed towards us, then the entire emission is confined into very narrow cone, and that gives rise to this relativistic beaming, and therefore this component is enhanced due to this beaming. And now if you apply general relativity, then the red wing of the line is gets extended to even lower energy, depending on what is the distance of this annuli from the black hole. If this annuli is closer to the black hole, this extension to the red wing will be stronger. Okay, and if you sum the line emission from all of these nuclei, then it looks like this kind of a profile, which takes into account your Newtonian special relativity, general relativity, etc. Okay, and this kind of line set was actually observed in 1995 for the first time using the Japanese satellite, advanced satellite for cosmology and astrophysics, and that was the first result, and it was matched very well with theoretical prediction. So this red wing here is coming from very close to the black hole, and one can study the shape of this red wing to probe the innermost regions near the black hole. Okay, so here is an example of a very high signal to noise data now taken with the New Star mission by NASA. The advantage of New Star mission is that it has a broadband coverage from 3 kV to up to about 80 kV or so. Here is what is shown is 3 kV to about 40 or 50 kV. And these are the data, you see this solid points. These are the data points, actual observed data points. And the blue line here is the model without any relativistic effects. if the line were coming from, let's say, coming from regions where there is no supermassive black hole, then the spectrum should look like this, like the blue line here. Okay, but this obviously does not match with the data. There is this broad iron line, and even the reflection hump is modified. But once you apply the relativistic blurring, then you describe the data very well, and clearly the reflection spectrum gets modified due to the effects of general and special relativity here, and this broad line you observe. And this is a Schwarzschild signature for general relativity here. And that is not the only object. So there are a large number of objects now. Yes.
Yeah, in the previous plot, so there are still discrepancy like around 18 kV and also at 8 kV, right? I mean, the data points, there are like excess emission at 18 kV, around 18 to 19 kV, and also at 8 kV. So, I mean, do people understand like why is that?
So you don't have to consider individual data points, because the data are, of course, have Poisson noise. So there will be some departure. Not all the solid points will be going along exactly with the model. That's impossible. Okay, yeah. So one can, of course, one can statistically qualify whether this model is good enough for the data or not. That way, the model describes the data pretty well.
I see, because I mean, it seems that systematically, around this 18 between 18 to 20 kV or 17 to 20 kV, all these points are systematically higher.
These are one. Okay, so there are slight higher, but all of these are within 1 sigma kind of thing.
Okay.
Okay, so these are not very strong evidence for anything else, I would say.
Okay.
But future, if you say, let's say, future at more advanced missions, if you observe and you really see excess emission, then of course one has to worry about that.
I see. Okay. All right.
Excuse me. So there is a there is a peak around this iron line region, right?
Yes.
So we are getting way less iron brightness than we expect. Is there any particular reason for it?
What do you mean by way less iron emission?
I mean, the line.
No, the blue one is actually unblurred. That is
okay, that is unblurred.
Yeah, that is anyway not explaining the data. Only after blurring that explains the data. The other curve here. Okay. So we have now large number of such objects where you see this broad iron line as well as the reflection hump, and that obviously has been explained with this reflection spectrum. But there were other possible models. I will not go into the detail, and that kind of gave rise to some kind of controversies. And but then there was very important discovery in 2009. So what was done? So this is again the data from European mission XMM Newton, and this is the ratio of the observed data and a very simple power law model. And what you see, so power law model was of course generated without using some of these bands where you see the excess. This was generated between 1 to 3 kV band and maybe lower energies one. So you see very excess emission at near 6 kV, which is obviously due to the iron K line. This is the iron K band, but also you see an excess broad line like feature at just below 1 kV, and that's due to the iron L line. So iron K line arises due to the transition from L cell to K cell, while the iron L line arises from a transition from M cell to L cell. So the importance of this iron L line is that in this band at soft excess, we have much larger collecting area compared to iron K band. Also, the background is lower at soft excess compared to slightly hard excess. So that means we have many more photons here near the iron L line. So therefore, one can study the variability. How does this reflection feature actually varies? That one can study, and that is what was done here. So one band was chosen which was dominated by this iron L feature, and another band which was dominated by the continuum emission. So one can think of the, okay, this is an illuminating band. Hard band is essentially the illuminating band, and the soft band is mostly consist of a reflected band. And then look at the relationship between these bands. So these people, Fabian et al., calculated the cross spectrum and the time lag spectrum. So what is cross spectrum? So one takes the light curve of these two bands, okay, then calculates the Fourier transform, and then multiplies this Fourier transforms, and therefore you have a complex quantity which you can have the phase and the amplitude. From the phase, one can derive the time lag, essentially phase divided by 2 pi times the temporal frequency. That becomes the time lag. And that time lag is plotted as a temporal frequency here. So what this plot tells us that the amount of lag is a function of time scale. For example, if you are looking at short frequencies, low frequencies, that means longer time scales. If you are looking at the variability on longer time scales, then it is the soft band which is leading the hard band. That means this particular band is leading this illuminating band when you are looking at the variability on longer time scale. While at shorter time scale, that means when you are looking at rapid variability, then it is the soft component that is getting delayed compared to the illuminating component or the hard component. And this delay is about 30 seconds. And in this particular case, this band is dominated by this iron L line. Of course, there is a continuum emission also. So this particular negative lag here is interpreted as the lag between the continuum emission and the reflected emission, which is the iron L line. So this is called the reverberation lag, and the reverberation lag one can measure only for rapid variability arising from very close to the black hole. Okay, this was a very interesting observation. And this has been confirmed with many ways. To understand a little more simply, so look at the light curve. So these are the light curves in different bands. So the red curve is in the soft band, 0.3 to 1 kV, and the blue curve is at the harder band, the 1 to 4 kV, where the 1 to 4 kV is more like a pure continuum, and 0.3 to 1 kV is more like dominated by this iron L line. And now if you look at the short time scale variability, so you see the x-axis is time, so 0, it starts from 0, 2000, 4000, like this. So one is looking at the short time scale. So in this case, you see the peaks of this, the soft band light curve in red, and the blue and the hard band light curve in this. So obviously the soft band is lagging behind. Okay, so what is happening then? The X-rays are illuminating, and then the reflection is arising, and that is lagging because there is some light travel time involved. So reflection emission should lag behind, and obviously it is lagging. But if you look at the longer time scale variability, in that case, it is the soft band which is leading here. Here it was lagging, here it is leading. And the general interpretation is that on longer time scale, it is the continuum component, not really the reflection component, which dominates for longer time variability, which we do not understand very well, but there are some models, but then I'll not go into the details. But on long time scale, so the continuum variability dominates, while at short time scale, it is the time lag measurements are dominated by the reflection emission. So these are the observations and time lag measurements. Later on, this kind of a lag was also observed for iron K band. Whatever I discussed was for iron L band in the soft X-ray band, but people later on found that the same kind of a lag is also exists for iron K line or iron K alpha line. So these are again, okay, these are now the lag spectrum is a function of energy. So this tells us, if you look at this curve here, this tells us the lag of the 2 keV photons relative to the entire band. So this means this is a negative lag. That means the soft X-ray, the photons at 2 keV are actually leading here. While if you look at here, then this is a positive lag. That means the photons at 6 keV are actually lagging behind the full band, which is dominated by the continuum. And this also, if you look at as a function of temporal frequency, that is the variability time scale. So for the fastest variability or the most rapid variability, where here you see the iron K-like line kind of a feature. So this is again clear signature for the iron K reverberation lag now. Okay, not only in the iron K line, but also this kind of lag is also seen for the reflection hump. And that you expect because the iron K line and the reflection hump are arising due to the same kind of physics. Both are reflection components. Okay, so the reflection component, of course, you measure around 20 to 40 keV, and this band also appears to lag behind the continuum emission or the entire band, which is dominated by the continuum emission. Again, yes.
Just one question,
Yeah.
small question. Yes, so the L line is also should be lagging by that sense, right? Because the L shell electron has similar emission mechanism like the K shell electrons.
Yes. So if you could extend here to sub keV, then that should also show. But this particular object is an absorbed agent. So below about 2 keV, the X-ray emission actually gets absorbed due to the torus. So here, when I mentioned the negative lag here, this is as a function of temporal frequency. Now one is taking at a certain frequency range and looking at the lag as a function of energy. So these two plots are very different. So but it can be confusing. Okay. So as I mentioned, if let's say if the X-rays were not absorbed in this region and one could observe the iron L line and at sub KVs, then you will also see a positive lag here at the position of iron L line at the iron L line energy. Okay. So you see lag in iron L line, you lag in iron K line, as well as in reflection hump. And this kind of establishes the reverberation lag and X-ray reflection in AGN.
And also from this lag, can we say something about the extent of the reflecting regions, or this reflection is expected to come from the disk, right?
Yes, the innermost regions of the accretion disk. So there is a light trial time effect as well as the size, the extent of that emitting region or reflecting region in the disk. Of course, with the detailed modeling that has been done, and again, this kind of the observations give rise to very compact hot corona.
Gulab,
yes.
I have a question. I'm not sure if I have understood it correctly.
Yeah.
So the short time variability, the soft photons are lagging. Is that correct?
Yes, in short time variability, for short time variability, the soft photons are lagging, and that's the reflect.
That's because of the reflection. Because
yes,
it takes some time. Right?
That's correct. That's correct.
And in long term, you are saying the continuum emission from the disk, which is going through some variation, and there the continuum, sorry, the soft emission is bleeding.
Yes. So let me give little more detail. So yes, the continuum emission here is in the X-ray band, and it is coming in the soft band, so the soft X-ray continuum, and that will be more likely part of the X-ray the componizing continuum. I mean that again that we clearly do not understand, but to qualitatively understand, let's say we have an accretion disk the outer regions of accretion disk are the obviously emitting this optical. And if you move inward, then you are getting this UV radiation, then and extreme ultraviolet, and finally soft X-ray regions and hard X-ray, etc. from the corona. So there is a model known as propagation fluctuation model. So what happens in the outer disk, this due to the variation in accretion rate, that variation is very, very slow. Okay. When you move inward, there is a fluctuation in the viscosity, and that modifies the variability of the shorter wavelength radiation. So compared to the optical radiation, the UV radiation will be varying faster, and then you go to the far ultraviolet, then extreme ultraviolet, they will be varying even much faster. And when you come to the X-rays, they will be varying even faster. So that kind of process is giving rise to in that sense, the softer X-rays will lead harder X-rays, or shorter the longer wavelength radiation will lead the shorter wavelength radiation, because the fluctuation is traveling along the accretion disk and finally reaching to the innermost region.
So this variability doesn't have anything to do with reflection.
That variability has nothing to do with the reflection.
Okay. Now I got it. Okay.
Yes.
Yeah. Thanks. Yeah.
Okay, so once people measure this iron K lag, because this is a time scale, okay, this is some kind of a time scale, and this time scale obviously should depend on the black hole mass. So people measure this iron K lag and plot it as a function of black hole mass for for a number of AGNs. Again, they see some kind of a scaling relation, which you expect due to the larger black hole mass should have longer time scales or larger size scales. This also has been established now. Okay, when you look at this lag energy spectrum, and here is a comparison for four different agents, and in the iron K band, you see the profile is very similar, and that is what you expect. But when you go to the soft X-ray band, there is a varying shape. So the shape of this lag energy spectrum varies quite a lot in the soft X-ray band. So the one question is this pure reflection, whether the soft X-ray emission is pure reflection, or there is some additional component which might be modulating this kind of thing. So that this question arises from this one, this kind of reflection spectrum, and there are other regions as well. So and if you look at some of the observations where you see very, very strong soft X's, but iron line, which is not that broad. You look at this object called Archelian for 120. Iron line is pretty weak. It is not very broad. I mean, a relativistic broad iron line will extend down to 5 kV or so. Here it is just around 5 kV. It looks like more like a narrow iron line rather than really broad iron line. But if you look at the soft axis of this agent, it's a very, very strong. Now, if the soft axis has to be reflection, then there should have been a very strong relativistic broad iron line, which is not the case here. And if you try to model with reflection model here, you cannot describe the entire soft axis as purely due to reflection. So this is actually the model. Here there is a relativistic reflection seen here in the gray line. There is a distant reflection, the torus structure which I mentioned, that can also reflect X-rays, but torus is quite far away, so therefore this is not modified. The reflection from the torus is not really modified by strong gravity there, so you see narrow emission lines from the torus. And when you include all these things, you need a strong black body kind of a component for the soft axis. So this component can arise due to comptonization in the inner regions of the disk. Okay, and that is another model for the soft axis. Just
a small question. In the previous slide, is this Compton downscattering all these peaks below say 3 to 4 kV, or is there are different lines altogether?
Oh, these lines. Okay, So these lines, let's say around 1.5 kV, 1 kV, etc. These lines are the reflection from the reflection spectrum. Because we have so many elements, and if they are not blurred, if they are arising far away from the region, so they are obviously not getting blurred. So the iron line also narrow here. So the narrow iron line and this discrete features are all due to distant reflection. While you see the other component, which is a relativistic reflection, there the iron line has got broadened. Even this soft X-ray lines have somewhat broadened. But because this line is not really strongly relativistic blurred, so you still see these features. Okay. Okay, so one can, there is another model for the soft X-ray axis, which is completely different from X-ray reflection. Okay, so here, yeah.
Gulab, 1 second. We are almost 1 hour into the talk. So how much?
Okay. Okay, so I will try to conclude in. I have quite a bit of it to discuss, but I will try to conclude in maybe next 5 minutes or so.
Oh, 5 to minutes is fine. Yeah. Okay.
Yeah. All right. So, okay, so I'll move a little faster. So this is the model for the soft X-ray axis, where the accretion disk is behaves like a standard Shakura-Sunyaev disk down to a radius of R corona. But below this radius, the disk is warmer compared to a Shakura-Sunyaev disk, but it's still optically thick. So if such a thing is there, then this warm disk in the inner regions will comptonize the emission from either from the midplane or from the disk below away from this R corona, and give rise to this kind of a soft excess emission, which may be the source of soft X-ray emission in some of the agents. And this is called intrinsic comptonized disk model or warm comptonization model. And such a model can be tested with AstroSat, and which we are actually doing. This is the same model, improved version of the same model, so I'll not discuss this. But the important thing is that because the inner region of the disk is actually emitting, actually it is not like a Shakura-Sunyaev disk, and it is emitting soft X-rays, and it is warmer. So that means this is not emitting the ultraviolet emission. So if you are observing the ultraviolet emission, then there should be deficit of ultraviolet emission compared to that predicted by a full standard disk. And that is what one can test, because we have ultraviolet emission from the UVIT. And this is one example. This is a Feral 9. This agent has a very, in fact, negligible internal extinction. So one doesn't have to worry about these things, the internal extinction here. This is a comparison of HST spectrum, optical, the UV spectrum taken by HST FOSS, and the FUV, UVIT, far ultraviolet and near ultraviolet grating spectrum. So they match pretty well. Of course, there is a variability, of course. And this is the dispersed image, ultraviolet image of this field. Okay, when you try to describe the ultraviolet spectrum, so and compare with the X-ray data, with a simple power law. So the X-ray is much lower in intensity. So that tells there is some kind of a UV bump, and that's the evidence for big blue bump in this agent. And in earlier studies using X-rays only, soft X-rays and hard X-rays, people have inferred a black hole spin of 0.97 by modeling the soft X-rays, either reflection, blurred reflection spectrum. And now, because we have ultraviolet continuum from the intrinsic emission from the accretion disk itself, so one can now test whether such a black hole spin is allowed, or whether this emission is really the standard disk emission. And in this case, it doesn't. I mean, the UVIT data is not consistent with a black hole spin of 0.97 here. And this is, if you fix the black hole spin, it looks like something like this. Okay, but one can model the entire UV X-ray, far UV, near UV, and X-ray data with this kind of a warm comptonized model, where the accretion disk is truncated at a radius of about 20 Rg, and below that there is this warmer accretion disk, which is giving rise to comptonization. And using this kind of model, one can infer a black hole spin of more like 0.5 rather than 0.94. This is one work which we are still preparing a paper based on this one. Okay, I think I will. I'm running out of time, so I will. Okay, maybe I'll mention only one thing and I'll stop. So one more thing, because there is a delay between the seed photons from
So
the.
2 minutes, okay, Gulab.
Yeah, all right. So there is a delay between the disk emission and the hot corona. So whether one can measure, so that one really know. This is a, I mean, whatever I had mentioned earlier is a theoretical model. But one needs to probe observationally, and we have probed in this AGN, Markinen 493. This is the work by Olu Asina, who was a PhD student at ISC, and myself and few others. So these are the UV and X-ray light curve, and when you cross correlate these, so it turns out that the UV is actually leading X-rays, and that is what you expect from Comptonization model. And these are the typical magnitude of this UV lead here, and one can measure this kind of lag and the uncertainty, etc., with the simulations which we have done here. These are the lag distribution, etc. The important thing is because UV is leading here, and the UV is arising at certain, let's say, some radius R, and then this UV radiation has to travel to the X-ray corona, and therefore the light travel time comes into picture, and then the UV photons have to go through multiple Comptonized scattering, and the sum of this light travel time and the Comptonization time, that is the if that is consistent with the observed delay, then one can say that this is due to the Comptonization itself. And we did all these calculations, and here we find that the sum of this light crossing time scale and the Comptonization time scale is very much comparable to the observed time scale, and therefore we kind of establish that the accretion disk is the entity which provides the seed photons. Here, with AstroSat observations also, we see very similar characteristic in another AGNs. Again, the UV, far UV and near UV emission leading the X-ray emission, and the time delays are consistent with what is expected from thermal comptonization. We have also studied the UV emission from this with multiple observations. In this case, if the UV is increasing, then it is supposed to cool the hot corona, and that has that we have observed in this particular agent. I'll not go into the detail in the interest of time. Okay, so I think I will stop here because there is not much time. Okay, I will go through the summary of this my presentations, and I'll leave it here. Thank you very much. I would like to thank my collaborators, particularly the AstroSat teams, the SXC team, UBIT team, LexPC CZTI teams, and my collaborators, Yossi Papadakis, Jan Mekari, Alex Markovich, and a number of students who work with me, are working with me, and postdocs. And I'll leave it here. Sorry for somewhat exceeding the time. Yes.
No, that's all right. Thank you very much for a wonderful talk. So we'll take more questions now.
Yes, sure.
Yeah, go ahead.
So I have a small question. So you said that there is a 7 kilosecond, total 8 kilosecond lag, correct?
Yes.
So multiplying that with the speed of light, is that how you are estimating the region where you are saying that this lag is occurring or not? Or
yeah. So with the from the standard accretion disk theory, we are finding first we calculate the temperature that will give rise to the radiation at that particular wavelength. Once we have the temperature, when that we convert into the radius, and once we have the radius, then we calculate by divide by light, speed of light, then the light travel time. So that is the light crossing time. Then we also calculate the comptonization time scale, because there let's say you are upscattering optical UV photon to X-rays, then the number of scattering required and how much time each scattering takes, that depends on the size of the corona. So doing all these things, then we are calculating the comptonization time scale, which is much shorter, about order of 1 kilosecond. And the sum of this is essentially should be comparable to the observed delays.
Okay, thank you. Thank you very much.
Yeah.
Okay, I have one question. Can I ask?
Yes, please.
Any other questions?
Hello.
Yeah.
Yeah. So in one AGN you showed this sub kV emission line around peaking around 0.9 kV, 0.8 kV.
Yeah, go
and,
on. We can hear
and,
you.
And you said that it is iron L line.
Yes.
So was it confirmed by RGS detection, or because there can be other elements like magnesium or oxygen also? So was it confirmed by RGS that it is iron L line, and that's how you are mapping the reverbation with iron K and reflection model?
Yes, it is confirmed. There is a peak in the RGS spectrum as well, but this is much broader. So there can be other emission lines in that band, but given the, let's say, one using the solar abundance, and then one can predict there what are the strength of the other emission lines and actually model that. And that around 0.9 kV iron line is the strongest line one expects there.
Okay. And when you are saying this line broadening, you are, when you calculate this, you are assuming this Maxwellian distribution to calculate this velocity of these particles.
The rotation is, one is using the rotation speed of the disk using the standard disk, and of course the strong gravity there.
So the weight is comparable to the weight, the velocity that you directly got from observation is comparable to the rotation velocity of the disk or not?
So it is actually broader, because one needs to apply general relativity as well, not just special relativity, but general relativity also. So just by rotational speed, the one cannot explain the entire width of the line profile.
And there might also be line blending, right? Because alpha 1 and alpha 2 are not resolved.
Though alpha 1 and alpha 2 are very, very close. So both are very close to 6.4 kV.
Okay.
So you don't worry about that, because the line is much broader.
Okay. So line blending is happening there.
Line blending is happening, but practically it is a single line for us.
Okay.
Gulab,
Gulab. Yeah, go on.
Yeah. So basically,
somebody was asking a question.
Yeah, this is Mindaran. Yeah. So while
hello.
Yeah, I think Biswajit, you are running a bit lag. I think there is a lag. But anyway, so I will go ahead, and so modeling this lag, one has to take into account the size of the corona also, right? So that is a significant uncertainty, right?
Yes. This is a very good point. And so far, people have assumed lamp post geometry, where the corona is assumed to be more like a point-like object.
I see.
And then one can explain, because general relativistic simulations using extended corona is much more difficult, but it has been done. And it has been done, and what the results are there, they are also consistent with the compact corona, not extending, making it very large.
Okay, I see.
But most of the time, the models are based on lamppost geometry.
Okay. So that is, I mean, the computation.
Gulab, there is a question in the chat.
Okay.
Gulab, there is a question in the chat.
Yeah.
In case of Ferrel 9, how is the spin? How is it concluded that the spin is not as high as it was thought from that?
Okay. This is again a good question. I did not detail it, and of course, in the when we are modeling the reflection emission, and then depending on the relativistic amount of strength of relativistic blurring, one is essentially calculating the inner radius, and that the inner radius obviously depends on the black hole spin. That is how one is doing when one is modeling using the reflected spectrum. In the other model, the warm comptonization model, it is completely different. So there, the disk spectrum requires the accretion rate, because the disk spectrum requires temperature of the disk that depends on the accretion rate. So accretion rate is one of the parameter in the model, and you can calculate the accretion rate, give to model the data. Once that is done, then you can calculate the luminosity eta m dot c square. M dot you are getting from the model, multiply with c square, you are getting luminosity. Only uncertainty is eta, the efficiency. Now the efficiency depends on the spin again. So for what efficiency, the observed luminosity, which is the broadband luminosity, which you are measuring by integrating the entire spectrum from the best fit model, and you are calculating the m dot also. So given the L and m dot, and find the value of eta for which spin the correct that eta is required, and from that you are measuring the spin in that model.
Okay, if there are no more questions, I will ask one.
Yeah.
Gulab, has there been any recent development in our understanding of the growth of supermassive black holes, or especially in the context of these variability studies? Do variability studies give us any clue towards possibility of radiatively inefficient accretion?
I am the variability studies. Okay, I'm not aware of such studies, but of course the radiatively inefficient accretion has been studied using a spectrum. Spectral, some of the spectral models. For example, in low luminosity AGNs, when people cannot use the standard disk model, and there again people see this deficit, and that people think that that's due to the radiatively inefficient accretion there. But using variability, I haven't come across such a thing. So you mentioned black hole growth also. So what exactly you wanted to ask from that? Biswajit, can you hear?
I got logged out, so I couldn't hear your answer at all.
Oh, okay. So what I was mentioning is that from variability studies, constraining the radiatively inefficient accretion, that I haven't come across. First of all, the variability process itself are not well understood. But on the other hand, people study radiatively inefficient accretion through broadband spectroscopy, particularly in the UV and X-ray, also X-ray. So there one cannot use the standard accretion disk models, and when they cannot model the data, and then they invoke radiatively inefficient accretion models, and that's how they try to constrain some of these things. But you mentioned black hole growth. You wanted to ask some related question on black hole growth or something, yeah, which I was not able to understand clearly.
No, that is where the interest was. If there is possibility of radiatively inefficient accretion, that might explain the rapid growth of black hole mass.
Okay. The material directly going into the black hole, and then yes, that is a possibility. But okay, so but black hole growth, at least in Asian cases, if you look at the most luminous quasars, which are really huge in their masses, just by accretion, at least from with the standard disk, that is not possible. You are right. I mean, if there is a very large increase in accretion rate in the ad hoc kind of the inefficient kind of scenarios, then it may be possible. But people invoke this mergers of supermassive black holes in those cases to form the really massive black holes, are the most luminous quasars. And those simulations people have done, and they can produce 10 to the power 10 solar mass black hole and all that with mergers, of course.
Okay, thank you, Gulab, for an excellent talk and very patiently answering all questions. And we look forward to actually you visiting us.
Yes, thank you very much. I will happy to be visit some other time. Thank you very much, Vishal.
Thank you.
Finally, I would like to ask everyone to just unmute their mic and clap for Professor Dewangan for this wonderful talk.
Thank you very much.
Yeah, we would have loved you in the campus.
Yes. So sometime I'll visit Thank you.
Yeah.
Okay.